In this section, 3.2, we're going to look at how to calculate confidence intervals for proportions, which essentially means what to do when we're dealing with qualitative data. You see, when we're dealing with qualitative data, the only statistics that we generally have available to us are counts or percentages. And so percentages are the same thing as proportions. And so anytime we're dealing with qualitative data, we have to do stuff with proportions. So that's what we're working on now. One thing we learned about proportions earlier is that probabilities based off of these qualitative values will often require the use of the binomial distribution. And so because of that, we're going to adopt a lot of the same notations from binomial distributions in this case. So for instance, P is going to be a proportion for a population that favors some event. That's going to be the parameter that we are estimating. X is the number of items in a sample that favor the event. Now this isn't the percentage, this is just the number of items. All right. N is the sample size. P hat, this is the proportion out of the sample that favors the event. That's going to be our statistic, or also what we know as our point estimate. All right, because recall that when we create a confidence interval, we have a center value, which is our point estimate. And in this case, the point estimate is P hat. And then we couple that with a margin of error. So this distance out to the outer endpoints of our interval here is our margin of error. And together that creates our confidence interval. So these values right through here are the confidence interval itself, the range of values that we expect the population proportion to exist on with some given level of confidence. So ultimately, we're going to need to know how to compute that margin of error in terms of qualitative values or having proportions involved. And so that is our goal here. One thing to keep in mind, P hat is X divided by N. So if you have 50 items out of a sample of 200 that favor some event, then your P hat is going to be, 50 out of 200 or 1/4 or 25%. Now, we know some things already about confidence intervals. That's all expected to be still in our memory. And it would be good if we could base a lot of what we did in the last section for what we're going to do in this section. And so one thing that differs, the main thing that differs right now, is the use of the binomial distribution for calculating probabilities rather than normal distributions. And it isn't just necessarily probabilities. You see, to our starting point in our process, we declared a level of confidence that we wanted to use. Based off of that level of confidence, we had to come up with a critical value, which meant we had to use the normal distributions in reverse. Now, some technology does provide a similar feature for inverse binomial distributions, but because it's not a continuous distribution, it's not really quite as robust. And so what we need to do instead is possibly come up with a way of using a continuous distribution in the place of the discrete binomial distribution. And that's where this next part really comes in handy. This is called the normal approximation to the binomial. And it says that if you have a binomial experiment, let me try that again. if you have a binomial experiment such that n times p is greater than or equal to 5 and n times q is greater than or equal to 5. Now, these rules right here are not always agreed upon. Okay. Sometimes you'll see the rule as n times p times q has to be greater than or equal to 10, or n times p has to be greater than or equal to 10, and n times q has to be greater than or equal to 10 instead of 5. And then sometimes I've seen rules stated where your p hat plus or minus your standard error has to be within 0 to 1. So there's different ways of defining this. I think the one I've seen most commonly in homework problems is n times p greater than 5, n times q greater than 5. Ultimately, these are just boundaries saying that if you meet these minimum requirements, then you should be able to estimate a binomial distribution pretty well with a normal distribution. Now, in order to calculate probabilities, you have to make a slight adjustment for the difference between a discrete and continuous distribution. It's accomplished by either adding 0.5 to x or subtracting 0.5 for x, just depending on if you have a left end or right end probability. It's not something you really have to worry about because you're not going to use this to calculate probabilities. You're only going to use this for knowing that you can operationally go through and use the normal distribution in place of the binomial in these cases, and then we're doing inverse calculations, not probability calculations. But I want to walk through a probability calculation just so you can see, how good of an estimate this really can be. All right, so we have an example, and we're first going to calculate that example using binomial distributions, and in that respect get the exact probability that we're supposed to come up with, and then we're going to do it with the normal approximation and compare the result. Okay, so suppose that 36% of the population has been vaccinated for a particular disorder. If we survey 65 randomly chosen individuals, what's the probability that more than 25 of them have had the vaccination? Okay, so we'll start using binomial distributions. All right, so either someone's had this vaccination or they haven't. We're picking people randomly, so these should be independent trials. And we have a fixed number of trials. We have 65 that are being surveyed here. So the number of trials is 65. The probability of success, which means they've had the vaccination, is 0.36. And what we're looking for is the probability that out of these 65, more than 25 have had the vaccination, so that x is greater than 25. Okay, so to do this, and I'm going to use the TI calculator here because this is older material and it's not something that you're expected to do in this section anyway. And you should be able to do this on your own technology since we've already learned this previously. All right, so the probability that x is greater than 25, so that's a right-end probability. We would calculate that then by doing the complement, which is 1 minus the probability that x is less than or equal to 25, making that a left-end and CDF style calculation. So this would be found by using 1 minus binom CDF, and we would provide to it n, p, and x. So n is 65, p is 0.36, and x is 25. So if I calculate this on the calculator here, let's see what we get. So 1 minus, and then go over here to binom CDF, 65, p is 0.36 and x is 25. That's 0.291. Okay. Now, if I do the same thing, but using a normal approximation, here's what I would do. So I'm working on now a normally distributed set of data. For every normal distribution, I'm going to need a mean and a standard deviation. Well, it just so happens that I have a way of calculating a mean and a standard deviation for a binomial distribution. The mean is n times p, which in this case, we have 65 trials, and the probability of success is 0.36. So n times p, that gives me a mean of 23.4. Okay, and then the standard deviation, we have a formula for that as well. That's the square root of n times p times q. So you should recall these just from the binomial distribution section. And in this case, that's going to be the square root of 65 times 0.36 times q, which is the complement of p, so 1 minus 0.36 would be 0.64. And if we put that into the calculator, we get, let's see, the square root of 65 times 0.36 times 0.64, 3.87. Okay, so now we have a mean and a standard deviation to work with. All right, so the mean of this distribution would be here in the center, 23.4. And what we're calculating is still the same probability. It's the probability that, let me scroll back up to show you, more than 25 have had the vaccination. So the number of people in this sample has got to be greater than 25. So it's still the same probability we're looking for. What that's going to look like here, 25 is somewhere over here to the right, and then or to the right of 23.4, obviously. And then we're calculating even further to the right of that, so beyond that value, because it's a greater than. So it would appear that what we would do then is we would calculate this using normal CDF, 25, and then E99, and the mean is 23.4, and the standard deviation is 3.87. So everything's looking pretty good, but let's just try this real quick and just see what happens. If you'll notice, I had talked about a continuity correction, and I haven't applied the continuity correction. So we're going to see what we get here without that continuity correction. This was 3.87. Sorry, I thought it was 1.87. Okay, so if I run this, I get 0.339, well, 0.340, which is not really all that close to this value right here, 0.291. So what gives? We're supposed to be able to get an approximate value, but that's not really all that great of an approximation. Well, there's a catch here. We can do what we're doing, but there's also this continuity correction. And let me show you with an app what I'm talking about. Okay, so here's a binomial distribution app which allows me to input values of n and p. So we have 65 trials in our experiment, and a probability of success is 0.36. So I'm going to put those values in. And what it's going to do is it's going to effectively, I'll just set this as 65 for now, that's the maximum. It's going to show me the entire binomial distribution here for this value of n and this value of p. In addition, what I can also do is I can tell it the boundaries of the values that I want it to compute the probability from. So for instance, we want to know the probability that x is greater than 25. So that region would be any number of people starting from 26 and then going to 65. So this shaded region right here is essentially the probability that I'm looking for. All right, I'm going to kind of zoom in on that region as best I can. One thing that you may notice here is that our distribution very much resembles a normal distribution, especially if we zoom in. And that is absolutely true. And another thing that's true is that normal distribution has a mean and standard deviation of exactly what we said in the homework set. Oh, shoot. And that mean and standard deviation, if we create a normal distribution based off of that, look how well that fits our binomial distribution. And so that's why, this approximation method, works as well as it does. Okay, here's the thing I want you to see. All right, so 24. Notice where the label of 24 is. It's right in the center of that bar. All right, you don't see a 25 because it's only labeling every other value for this many values along the x-axis, but this is the 25th bar. 25 is directly in the center of this bar, so if you just kind of imagine a straight line right through here, then if I calculate the probability that x is greater than 25 for the normal distribution, it's going to start right here and calculate the area going this way. If you'll notice, there's a gap between 25 and 25.5. That area is not really included in the normal distribution, in the binomial distribution calculation. It would be in the normal distribution, and so that's why we need this continuity correction factor. And it just says, instead of starting the normal distribution calculation at 25, start it at 25.5, which is the beginning of this bar right here. And that more resembles the shaded region here for the binomial distribution. So that's ultimately why we need this. So let me go back then to the notes and see the effect. Okay, so instead of going from 25 on, we're going to go from 25.5 forward. And we'll calculate that normal probability instead. So if we run this, we get 0.294, which is a lot closer to the probability that we were supposed to come up with, which is 0.291. So that continuity correction is important here. But that's just there to show you how well normal distributions can approximate binomial distributions. And because of this, we can use, under those given conditions, that n times p and n times q are both greater than or equal to 5, which in this case, it's not even close. Like n is 65, p is 36. If you multiply those two together, 0.36 times 65 is what I meant. Well, I guess we already did it with calculating the mean, but 23.4, that's much bigger than 5. So it's not even close. And then 0.64, which would be q times 65, is even larger because, well, 0.64 is larger than 0.36. So these are both clearly much bigger than 5, so it meets those criteria. And when that happens, the normal distribution is a very effective way of calculating binomial probabilities, which is great because then we can use this process for using the inverse norm in our calculation for confidence intervals of proportions. Now, the way that's going to happen is exactly the same way that we did it with, the confidence interval for means. We will declare some level of confidence, C, and then we'll balance that about the mean. Well, I guess we would balance it about the center, which would be a proportion now, but it'll be balanced. And then that's where the 1 minus C divided by 2 comes in. That gives you the area in the lower end of the distribution. So same thing it was doing before. So we know our distribution can be approximated with the normal. We declare what we want the level of confidence to be, which is going to be balanced about the center of the distribution. So this area here is our level of confidence. If you take 1 minus that value, it gives you the area in both tails. But if you divide that by 2, it gives you the area in just one of these tails. So this is 1 minus C divided by 2. And if you put that value into inverse norm, what you're going to come up with is the critical value associated with it, and that's what we're looking for. Now, it will initially be a negative number, but we'll just take the absolute value, just like we did in the previous section. Next, we need to compute a margin of error. And in order to do that, in general, what we do is we take our critical value and we multiply that by our standard error for whatever type of statistic that we're working with. If we're working with proportions, we know that the standard error for proportions from a previous lesson is the square root of p times q divided by n, which is related to the standard deviation of a binomial being the square root of n times p times q. But this is the standard error for proportions, and let me make this symbol look a little nicer here. It's supposed to be p hat. And that's why the formula for the margin of error here looks the way it does. It's z sub c, that critical value, times the square root of p hat times q hat over n. Now, we're using p hat and q hat in this case only because p and q wouldn't exist. You see, the thing is, we're trying to estimate the value of p, which is the population proportion. If we're trying to estimate it, we don't know the value. And so if we don't know the value, we can't use it through our calculations. So we substitute p hat here and q hat accordingly. And once we have that margin of error, then it's just a matter of creating our confidence interval, simply what we said at the beginning of the lesson, by taking p hat plus or minus that margin of error. Let's take a look at some examples. A survey distributed by Statista.com asked U.S. residents about their access to Netflix using their own account or a shared password. According to the survey of 2,200 respondents, 836 indicated that they had an active Netflix account and do not share their password with anyone else. Create a 90% confidence interval for the proportion of U.S. residents that have a Netflix account and do not share their password. All right, so as always, with any problems, look to what you're being asked to do because it often gives you a lot of hints to get you started along the way. So down here toward the end, it's asking you to create a 90% confidence interval and then continues to say, for the population proportion. And so it tells you very much what it exactly wants you to do. So we want to create a confidence interval. For any confidence interval, that's going to require basically 3 steps. The first step is to get your critical value. Once you have that critical value, you then need a margin of error. And finally, you create your confidence interval. Now, these are the same steps, whether we're doing a confidence interval for proportions or a confidence interval for the mean. It's just how we come up with the critical value or the margin of error might be slightly different than from one case to the next. All right, so we're doing a confidence interval for a proportion. So let's get started with the critical value. All right, so the critical value, this was the same formula here with respect to proportions as it was with the mean. It's just the inverse norm, 1 minus the level of confidence, and we're being asked to use a 90% level of confidence, so 1 minus 0.9 divided by 2. We put that value into inverse norm, and then we take the absolute value. Now, this is something from a previous section, so I'm going to use the TI calculator here. If you're using a different type of technology, you should know how to use it for this operation at this point. All right, so we'll do inverse norm. Whoops. The area that we're using here is 1 minus 0.9, which would be 0.1. And then we divide 0.1 by 2, that's going to be 0.05. All right, so just so you see that calculation, 1 minus 0.9 is 0.1. So 0.1 divided by 2, which is 0.05. So I am in fact doing absolute value, inverse norm, 0.05. Okay, then this is on a standard normal distribution, so I'm leaving mean and standard deviation the same. Left tail oriented here because, like I said, not everybody has the option to change these. So paste that in. So negative 1.645. And then we take the absolute value and it becomes 1.645. All right, so that's our first step, getting that critical value. The second step is the margin of error. And the formula for the margin of error, it's basically always the same. It's the critical value involved that we just came up with times the standard error for the statistic that we're working with. Well, the standard error for the statistic that we're working with in this case is the square root of p hat times q hat divided by n. So we need to figure out these values. We just came up with z sub c, the critical value, that's 1.645. All right, but we need to figure out p hat, q hat, and n. Now p hat, this is the percent or the proportion out of the sample that favors our event. So we have 2,200 respondents in this survey, so that is n. All right, and in the survey, 836 indicated that they don't share their password. So the number of people that favor our event is 836. So 836 over 2,200, that's going to be the value of p hat here. And we may have to round that. Let's see what happens. Oh, that works out as exact value, 0.38. If you need to round it, take it to a few decimal places, maybe more than you normally would, just to make sure you get enough accuracy in the final answer. All right, so that would be 0.38 for P. Okay, Q then is the complement of P. So the complement of 0.38 is going to be 0.62. And then we divide that by 2200. And that is our sample size, of course. All right, so all of this goes into the calculator. So 1.645 times the square root of 0.38 times 0.62 divided by 2200, and that's 0.017. So then our last step here is to come up with our confidence interval. And our confidence interval here, it's always basically the same, the way we construct this. It's whatever our point estimate is, and our point estimate changes here because we're dealing with proportions. So it's not a mean, it's the percent out of the sample that favors the event, plus or minus that margin of error, which we just got from step 2. So p hat is 0.38. The margin of error is 0.017. And so if we add and subtract that value from 0.38, that would be 0.363 and 0.397. So my confidence interval then looks like 0.363 less than P less than 0.397. So what we're saying is with 90% confidence, we are certain that the actual percentage of people who have an account but don't share their password is somewhere between 36 and 39% effectively. Okay, the next example here. The American Academy of Dermatology collects a random sample of 895 people who have been exposed to poison ivy and finds that 85% of them develop a rash. Construct a 95% confidence interval for the population proportion of people who are allergic to poison ivy. Okay, so again, look to what you're being asked to do. So you're being asked to construct a 95% confidence interval. And again, it goes on to say to do that for a proportion. So you already have a pretty good idea of exactly what you need to do. Now, to do this, there's some basic things that you need. You're going to need your level of confidence, which in this case is 95%. You're going to need your sample size, which is 895. Generally, you would need X. X is not provided in this problem because it says here 85% develop a rash. So if we're saying that a success is that somebody gets the rash, which if you had poison ivy before, that's not a success. But remember, there's no positive and negative connotation to success and failure here. It's just, it is the thing that we wanted to observe, or it's not the thing that we wanted to observe. But 85% developing a rash, that's saying that P hat is actually 0.85. So 85% of the 895, it's actually already computed P hat for us. In the previous example, we had to calculate P hat ourselves. This time, we have P hat. And if we wanted to figure out what X is, if 85% of our sample developed a rash, then 85% of 895 is effectively 760, we'll just say 760.75 for right now. All right, because we might need to round later on. If we do, we can, but we may not need to round. It just depends on where we plug stuff into the formulas. All right, the first thing that we do here is we get our critical value. So the critical value, again, is found by doing inverse norm, 1 minus our level of confidence, which is 0.95, divided by 2. Now the 1 minus 0.95 divided by 2, that's going to be 0.025. So we're really doing absolute value inverse norm 0.025. All right, so let's get that. Okay, inverse norm 0.025, and that's going to be negative 1.96, which becomes positive when we take the absolute value. Okay, so then our margin of error is the next step. We would take the 1.96 and multiply it by p hat, which is 0.85, that was given, times q hat, which would be 0.15, because that's the complement of p, divided by our sample size of 895. And so, let's see here. 1.96 times the square root of 0.85 times 0.15 divided by 895. So that's 0.023. Okay, and then once we have our margin of error, we can then come up with our confidence interval. By taking our point estimate plus or minus that margin of error. So the point estimate in this case is p hat, which is 0.85. We're going to add and subtract 0.023 to that, and let's see what we come up with. So 0.85 minus 0.023, and 0.85 plus 0.023, so we get 0.827 and 0.873. Okay, so that is how we construct the confidence interval, and these are the steps involved. All right, so the same 3 steps as the last type of confidence interval. And I want you to know and understand these steps, and I want you to be comfortable with using these formulas, because there will be test questions that will, specifically be designed to make sure you know these, the way these are done. But the online stats calculator also provides some additional features to create confidence intervals. And the way that's done, just like before when we did confidence intervals for the mean, we go to the estimates submenu here, and there's a bunch of different options for the types of estimate that can be computed. We are looking for the confidence interval for a proportion, so that would be the 3rd item down here. Now it takes 3 inputs. That first input, x. So here we would need to put this as 760.75, and I believe it will take it as a decimal. N is 895, and level of confidence here is 0.95. All right, let's see if it yells at me for the non-integer value. Okay, it does not. It's actually fine with that. That's great. The reason it's okay with that is because if we had to round it to the nearest integer, which if you think about it, you can't really have 0.75 of a person developing a rash or not developing a rash. It needs to be an integer. But the thing is, p hat was given as 0.85, and 85% of 895 just happens to be a non-integer value. So it is what it is. We'll leave it as that to make sure we get the same answers. The endpoints of this interval, 0.827, just like we had, and 0.873, just like we had as well. It also gives some breadcrumbs along the way. The level of confidence, 1.96. I'm sorry, not the level of confidence, the critical value based off of our level of confidence, 1.96, and the margin of error, 0.023. Okay, the next thing that we need to discuss here is what's known as the minimum sample size. All right, so suppose you create a confidence interval, all right, but you look at your confidence interval and you think to yourself that it's too wide. You know, we did all the work required, but the result is just too wide. So what we would like to do is make that confidence interval be a smaller width. Well, one way to decrease the width of the confidence interval is to decrease the level of confidence. All right, so that's not necessarily a great solution because, you know, you go from having, say, 95% confidence in your result to 60% confidence, and like that's just not really as reliable as a result. So that's not the best way to reduce the width of your confidence interval. Another way is to increase the sample size used. If you increase the sample size, that's also going to decrease the width of the confidence interval because the margin of error gets reduced, but it doesn't change the level of confidence. You stay at the same level of confidence. And this is such an important thing that statisticians will often, decide first what sample size is going to be appropriate to use for a study from the outset, so that they will achieve the results that they're looking for. They'll get the level of confidence that they want and have a width of a confidence interval that is sufficient to what they desire. In order to do this, we still use the margin of error formula. So this is the margin of error formula with regard to confidence intervals for the mean. And the thing is, you have the two variables here involved. You have n, and you have your margin of error. If you algebraically manipulate this and solve it for n, so for instance, if you multiply both sides by the square root of n, you would have e times the square root of n equals z sub c times sigma. Then if you divide both sides by e, you get the square root of n equals z sub c times sigma divided by e. And to get n by itself, you could square both sides and say that n is z sub c, the critical value, times sigma over e altogether squared. And that is the formula that we're looking for. So that is a formula for the minimum sample size required to keep a certain level of confidence and rein in the length of the width of your confidence interval. Now, this formula requires the values of three things. So you need to decide, what the width of your interval is going to be, your level of confidence, but you would also need to know what the value of your standard deviation is. And if you haven't done your study already, that's a rather difficult thing to actually know. So we generally would estimate the value of the standard deviation, unless it happened to be known from previous studies, for instance. And it's pretty common to use what's known as the range rule of thumb. And the range rule of thumb estimates a standard deviation, and it just takes the range and divides by 4. So the standard deviation is, I should use, approximated by the range of a data set divided by 4. And the reason that this works is the range is considered the, extents of your distribution. So you shouldn't have any values below a certain minimum or above a certain maximum. So that gives you the range, or the extent of all your data values. And if you think about the empirical rule says that 95% of your data is going to occur within 2 standard deviations of the mean. So if you don't think about all the extents of your data, you don't think about the extreme values, you just think of the bulk. So 95% is going to happen within 2 standard deviations. So if you just take your range and divide it by 4, it basically breaks your data into 4, parts based off of that 95%. That's kind of the idea. So the range divided by 4 gives you a good estimate for a standard deviation to work with. All right. You can also do the same sort of thing with proportions. All right, but what you have to do here is solve for n, again, using the margin of error formula for proportions. And if you solve for n, you get n equals p hat times q hat times z sub c over your margin of error quantity squared. And again, you do have to have a preliminary estimate for p hat. If you have a value, that's great. If not, then what you can do is similar to the previous, using the range rule of thumb, you just use p equals 0.5 and q equals 0.5. And this, in fact, kind of maximizes the value of n that would be used. And so, it's kind of like a worst case scenario. This is the sample size you should use. All right, a wildlife manager wishes to estimate the mean length of fish in a large lake to within 1 inch with 80% confidence. Estimate the minimum size sample required. In his experience, virtually no fish caught in the lake is over 23 inches long. Okay, so focus in on what you're being asked to do. You're being asked here to estimate the minimum size sample required for this study. All right, we're talking about the mean length of fish, so it's the minimum sample size for the mean. So the minimum sample size for the mean would be n equals z sub c sigma over e quantity squared. So we essentially need to figure out these 3 values and plug them into the formula, and then we'll be done. All right, so z sub c, that should be easy. This is the same critical value that we would use for developing the level of confidence, or taking the level of confidence and creating and getting the critical value. So inverse norm, 1 minus our level of confidence, which is 80% in this case, so 1 minus 0.8 divided by 2, and so we'll just use the calculator for this. And again, I'm just going to use the TI here because you should be, this is from previous sections, and you should be able to do this kind of a calculation no matter what technology you're using at this point. So 1 minus 0.8 is 0.1. 0.1, nope, sorry. 1 minus 0.8 is 0.2, and when you divide that by 2, that gives you 0.1. That's what I was thinking there. Mean and standard deviation, 0 and 1 respectively, tail set to left, and negative 1.28, which we'll just round to, or we'll just make positive. So positive 1.28. All right, sigma. That is the standard deviation. Well, the standard deviation isn't given because, like, we haven't done the study. So if we haven't done the study, we don't have any kind of estimates. But we are given this clue here. In his experience, virtually no fish caught in the lake is over 23 inches long. So this is kind of like the maximum length of a fish. The minimum length, I think we could just say 0. All right, it's not going to be anything less than that. But that gives us a range. So the range of the lengths of fish here would be 23 over 4. And so using the range rule of thumb, that gives me 5.75 for my standard deviation. Okay, it's an estimate. It gives us something to work with, so that's fine. The margin of error should be stated somewhere in the problem. All right, so the wildlife manager wishes to estimate the mean length of fish to within 1 inch. So it wants the real value to within 1 inch, so the margin of error is 1 here. All right, so the minimum size sample then is going to be 1.28 times 5.75 divided by 1 squared. All right, so let's see what we get. So 1.28 times 5.75 divided by 1, and then squared. So 54.16, and this is another time where you do kind of have to override the standard rounding rules, because if you go down to 54, you don't quite get the results that you're looking for, so you always round up. So this would be a minimum sample size of 55. Remember, always round up. Okay, but that's what we would do. Last example here. A government agency wishes to estimate the proportion of drivers aged 16 to 24. Sorry, the dash didn't come through there. Who have been involved in a traffic accident in the last year. It wishes to make the estimate to within 1 percentage point and at 90% confidence. Find the minimum sample size required using the information that several years ago the proportion was 0.12. Okay, so look for what you're being asked to do. You're being asked to find a minimum sample size required. So the minimum sample size, we have a couple of formulas here for minimum sample size. It's based off of the statistic used. In this case, we're dealing with proportions, so we want to use the proportions formula. So then that's going to be n equals p hat times q hat z sub c over the margin of error altogether squared. Okay, so we need to figure out the individual values here and then plug into the formula. Okay, so p hat. The thing here is we're trying to figure out, what the proportion actually is. We're trying to come up with this proportion. And so the thing is, we haven't actually done the study, so we don't have any values from the study to use. What we do know is from a previous time, the proportion was 0.12. So we're going to use that as our estimate, just so we can get the hit the ground running here, and actually do a calculation. Q then is always 1 minus P. So 1 minus 0.12 would be 0.88. Okay. Z sub C, that's no big deal because we would be using the same formula for the critical value here that we've been using. It's the absolute value of the inverse norm, 1 minus our level of confidence, which is 0.9 over 2. And so that would be 1 minus 0.9 over 2 is 0.05. And then we put that into inverse norm. And we come up with 1.645. Okay, and then the margin of error. So we wish to make the estimate to within 1 percentage point. So it's 1%, but we can't plug in a percent as a value. So we have to change this to a number, so 0.01. Okay, so we have everything we need. So this would be 0.12 times 0.88, and then 1.645 divided by 0.01 quantity squared. So we just plug this directly into the calculator of our choice. So 0.12 times 0.88. Let's see, I'm going to do this part in parentheses just to make sure everything's fine. 1.645 divided by 0.01 quantity squared. All right, so 2,857.56. This is a time where we do have to always round up. So I'm going to round here to the nearest integer because we can't include someone 0.56 of someone. So we'll round, but we'll always round up. So 2858. So 2,858 people need to be in this study. Just as a reminder, you always round up for these things.